All right, welcome to the second half of 1.2. We're going to be dealing with the rest of the properties of functions. Let's just go ahead and begin. Nothing extra to say here. So as mentioned, there's many different things that we can look for on functions. And after all of those things from the last video, the next one we're going to look at is the idea of an extrema. An extrema is it basically means just an extreme point. And the kinds of extreme points we can have are things like maximums and minimums. So the first one we're going to look at is what's called a local maximum. And what a local maximum is, this is something you might not have heard of before, but it's a maximum point on some open interval of f of x. So if I was to take a graph like this and go like so, this is a pretty straightforward quartic function. And if I was to look for a maximum or a local maximum represents some point that's higher than all of the points around it on both sides of it. And we do have a local maximum right here. This would be called a local max because everything to the right or everything close to the left and close to the right is below that point. So we have a local maximum. We can actually, using our calculators, we can determine this maximum point if we have the equation. Likewise, we have the idea of a local minimum, and with the same kind of definition, except for it's on as a minimum, not a maximum. So we have two of those in this case. This is a local min, and this is also a local minimum. Now those are local, meaning they're nothing too special other than the fact that they are maximums and minimums to the individual areas right there, those little spots. But we do have these things called absolute maximums. Absolute maximums being the very highest point or the maximum point on the entire domain. Now in this particular function that I graphed has no maximum point because this keeps going up and this keeps going up. So therefore there is no absolute maximum, but there is an absolute minimum. This right here, this particular minimum, we can also call it the absolute minimum. It's also called the absolute minimum. All right, so we can use our calculator to calculate minimums and maximums. We can determine if they're absolute and or local. We use these max and min points to actually help us on increasing and decreasing. Notice that it would be decreasing from negative infinity up until the x-coordinate of that, increasing from between these two x-coordinates, decreasing between these two x-coordinates, and increasing from this to infinity. All right, next, we are going to deal with symmetry. Symmetry just meaning symmetry, really. I mean, you've done this since elementary school. Can you fold the shape down a line and get the same thing on both sides? Can you rotate it and get the same thing? That's the idea behind these, but we have special names for them. If you are symmetric about the y-axis, that's the how, and this is what it's called. It's called an even function. You may have heard this last year in Algebra 2. So if I gave you the function, actually I have examples in a couple minutes, or in a couple seconds here. If I was to plug in a negative x and get out the original equation, so this means plug in the opposite of x. If it gets out the original equation, then it is even. Likewise, we have about the origin. This is an odd function. And an odd function, if we plug in the opposite of x, we get out the opposite of the original equation. So that's our two main ones. We have even and odd functions. But we also have the other type of symmetry, and this is about the x-axis. These are non-functions because they would fail the vertical line test. But this says if you plug in negative y into your equation, you get out the original equation. That's symmetric about the x-axis. Not too many of these. We can do them, but there's not too many. So let's start with the first one. I want to check the symmetry. So I want to check if it's symmetric about the origin. I basically want to know, is it even or odd? And actually, I don't even care about that. Let's scratch that for just a second. I'm going to ask it a different way. I'm going to say, what type of symmetry is it? And you notice that even and odd symmetry actually deals with the same exact thing. If I was to plug in the negative x. So let's do that. Plugging in negative x squared minus 3, I get negative squared is positive minus 3, and that's exactly the same equation as I started with. And since that is the case, this is an even function. Let's try it again. Does it have symmetry? Plugging in negative x. I get negative x squared minus 2 times negative x minus 2. I simplify this down. I get x squared plus 2x minus 2. That is not the same thing because it has a plus where the minus should be. This is a neither. It is not the opposite of the original equation, and it's not exactly the same as the original equation. Therefore, it doesn't have any symmetry. And lastly, down here, we're going to say, I guess this was called g, wasn't it? H of negative x. We're going to plug that in, and we're going to get 4 minus negative x squared. This x becomes just a positive x squared. This becomes 4 minus what becomes a positive x squared. You notice that that is exactly the same as before, and therefore it is even. Here's what an odd function would look like. I didn't choose an example here. Let's call it x cubed. If I did m of negative x, I would get negative quantity x cubed. And if I cube a negative number, it's going to remain negative on the cube. And notice that this is the opposite of what I started with, and therefore it is odd. Okay, moving right along, we're going to look at asymptotes. Asymptotes are, especially vertical, are based really on our domain. Vertical asymptotes. Whatever makes your denominator equal to 0 is your vertical asymptote. Something along this line. Oops, I graphed the equation first. If I have x minus 1 in your denominator for the function f of x, writing stuff backwards for some reason. If I plugged in x equals 1, that can't happen because it makes a 0 in the denominator. That would be a vertical asymptote. It would technically graph like this. As x approaches this 1, or if we call it an a value, as x approaches a, it goes to infinity. The function itself is going to infinity in either direction. My asymptote is since it's vertical, x equals a, or in the case that I gave, in the case that I showed, my vertical asymptote is x equals 1. Horizontal asymptotes are actually talking about what happens as x gets really, really big. As x approaches infinity or negative infinity, f of x approaches a single value, b. So if we had some sort of function like this, here's b. The function comes down and it gets really close to that dashed line, but doesn't become the dashed line. Same thing in the other direction. That would be a horizontal asymptote, and the asymptote is y equals b. Now, you might remember how to find the asymptotes from Algebra 2, but I put it down here just in case. And it's all based off the degrees of the exponents, or the polynomials that you're going to be dealing with. Something like this. This is going to have a horizontal asymptote. It's also going to have a vertical asymptote. If the numerator, and I'm talking about degrees, if the numerator is bigger than the denominator, which is not this case, it would be something that would look like x to the 5th, blah, 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 over x to the 3rd, blah, 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 blah. There are no horizontal asymptotes in this case. We'll get to what they are later, but there are no vertical asymptotes or horizontal asymptotes. If they are equal, so in this case, if you had a 3x squared plus 7 over a 4x squared minus 1, the horizontal asymptote is the leading coefficients of your polynomials, your numerator and denominator. In this case, my horizontal asymptote would be 3 over 4. And last but not least, the other version is if the numerator is less than the denominator, like the first one that I drew, then the horizontal asymptote is automatically 0. So let's go ahead and find a couple. Let's find all of our asymptotes. So for f of x, my vertical asymptotes, anything that makes the denominator 0, well, it might be handy to factor said denominator to x minus 2 and x plus 1. Well, that means my vertical asymptotes are x equals 2 and x equals negative 1. Horizontal. I look at the degree. This has a degree of 1. This has a degree of 2. Denominator is bigger, and therefore y equals 0. G of x is a little bit different, though. Vertical asymptotes usually come from whatever x cannot be, but x can be anything, so we're going to say none. Horizontal asymptotes, however, are a little bit tricky on this one because you need to understand what that function looks like. This function looks like this. As x gets really, really small, going towards negative infinity, it's approaching 0. So my horizontal asymptote is going to be y equals 0. That's for g of x. For h of x, vertical asymptote, anything the denominator is 0. Well, in that case, it's just 0. My horizontal asymptote, the degrees are equal. They're both 1, and therefore it's the ratio of, oh, that's not a 0. They're the ratio of the leading coefficients. In this case, they're 1 and 1, and therefore the equation is y equals 1. Lastly, for m of x, vertical asymptote, x equals negative 3. And my horizontal asymptote, since the numerator is bigger than the denominator, it would be a none. Wow, that's an ugly none. There is a different type of asymptote here, but we're not going to cover that just yet. Okay. Whenever it asks about end behavior, it's basically asking about asymptotes or what's happening as x gets really, really big, what is happening to y. So some of these are going to be asymptotes, horizontal asymptotes. Some of them are not going to be. But here's what I'm going to get at. For f of x, the end behavior is this. As x, we're going to write it like this. As x goes to infinity, notice that this has a horizontal asymptote at 0. That means as x goes to infinity, y goes to 0. As x goes to negative infinity, y goes to 0. And you can look at that graphically or just know the whole thing about horizontal asymptotes. For g of x, as x goes to infinity, y goes to, well, in this case, my horizontal asymptote is 3. So it goes towards 3. Likewise, in the other direction, negative infinity, y goes towards 3. Now, here's what's interesting on h of x, or let's call this an m. H of x and m of x. I don't have any horizontal asymptotes, but I still have end behavior because it's talking about what happens on the right-hand side and the left-hand side of my graph. Here's what we can do. We can kind of think about this 1 as a non-existent entity. And we have x cubed over x. Well, this basically becomes 3x. If you do x cubed over x squared, it becomes an x, and you're left with the 3 in the numerator. Well, that function looks like that, which means as x goes to infinity, y goes to infinity, because as x goes bigger, y goes bigger. And as x goes to negative infinity, y goes to negative infinity. Likewise, we can do the same thing with this m of x. The x to the fourth and x to the squared kind of cancel. They don't really. Don't get that mistake wrong there. It kind of looks like a 3x squared, which would look like this. And it just happens that x, as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative or positive infinity. Because on both sides, it's going up on both sides. Okay, I think that's going to cover it for section 1-2. 2 little short videos, but a lot of things to cover. So we're going to be going through this quite a bit, especially section 1.2. All right, I hope you guys learned something. I will see you guys tomorrow.